There's a clock there and back there as well. Some water. Okay. Good afternoon and welcome everybody to today's press conference where we will unveil the results achieved by the Global Scientific Consortium Event Horizon Telescope, which aims to capture the first image of a black hole. A very warm welcome to all of you, especially those who have traveled from across Europe to be here today. We have very little time before the actual announcement goes live across the globe in 6 simultaneous press conferences, so I will break with protocol a little and hand the floor directly to European Research Commissioner Carlos Moedas, and then we will turn to the 5 leading scientists here on stage with us involved in the discovery. Commissioner?
Thank you very much. Let me put the timer. Thank you so much, and it's a great honor to be here today. We're really about to announce a huge breakthrough for humanity. We are about to take a picture of something that one man alone, dreamt, imagined 100 years ago in 1915, Albert Einstein. Imagine that. This idea that a very big weight transforms geometry, that when the mass is too heavy, you make a hole, a mysterious hole, where nothing can get out of it, where all is absorbed. Michael Kramer here from the ERC said, the history of science will be divided into the time before the image and the time after the image. And you know, for my generation, it's all about the imagination of something that was in between science and fiction. At the age of 9, I went with my father to watch the movie Black Hole. And I remember coming home and for the first time in my life, 9 years old, thinking about what's the meaning of life? What am I doing here? Is there any parallel universe? That's what really got me excited. And probably the question that we have to ask to us, to everyone here that really loves science, is to think about, what about in 100 years? Einstein was there 100 years ago, but in 100 years, what have we and what will be the discoveries? The things that we'll discover from this knowledge. You know, I see Robert de Graaf there that wrote a great book about the usefulness of useless knowledge. And Einstein could not imagine, he could not imagine what he discovered. He cannot imagine that one day, because he created and discovered the antimatter, that would create the PET scan that will save lives all over the world. So I'm really proud. I'm proud of science. I'm proud of science because science today is giving a lesson to politicians. It's showing that today to take a picture of something that one man dreamt 100 years ago, you need people from 40 different countries. You need people from all over the world, that at the same time that you're sitting here, there's 6 press conferences in Washington, in Tokyo, in Taipei, in Shanghai, and in Santiago de Chile. And I'm proud of Europe. I'm proud of Europe because we have invested so much in this project. We have put altogether more than 44 million euros because we can be proud that Europe has a winning formula. And that winning formula is simple. We believe deeply in the freedom of science. We believe that scientists are the ones to make the choices. that the choices of science are not done by politicians. We believe somehow in the intuition of science. Stephen Hawking once said something that I would like to finish these words today with you, with this excitement of us. He said, "It is said that facts are sometimes stranger than fiction, and nowhere this is more true than in the case of black holes. Black holes are stranger than anything dreamed up by science fiction writers, but they are firmly matters of science fact." So, ladies and gentlemen, I think that I've not been this excited since when I came in 2014. If there's a big moment for all of us, it is today. And so this big moment is shared with so many in the public, so many today here, and I want to invite all the team. And for that, Professor Heino Falke is here, so he will come immediately to my place and tell you, and we will join all of us here in the room, we will join him unveiling the image. So Professor, please come and I'll go.
I still have to, thank you. Now I have to fill the time actually until we're allowed to actually, start the unveiling sequence.
Introduce yourself and your team.
I thought I use the time to introduce our team here that's here today on stage. We have Monika Moshi-Broczka from the Radboud University, working on theory and imaging of black holes. Luciano Rizzola from the Goethe University in Frankfurt. We have Eduardo Ros from the Max Planck Institute for Radio Astronomy. And we have Anton Census, the director of the Max Planck Institute for Radio Astronomy in Bonn, and also chair of the board of the Event Horizon Telescope. And we have, a lot of team members here in the front row. Michael Kramer was already mentioned, our co-PI. You have Remo Tilanos, the project manager of the Event Horizon Telescope. I'm glad you're here with us today. Colin Lonsdale, who is the co-chair of the Event Horizon Telescope project. Now we have to start with the session. We are looking into space, towards a galaxy, a giant galaxy, 500 billion light years away from us. Sorry, 500 billion kilometers away from us. Very big galaxy which was suspected to host a supermassive black hole in the very center. 101 years ago, someone discovered a streak of light, which is plasma shooting out of the center of the Milky Way, marking the supermassive black hole. I never believed that this black hole was as big as people said, until we saw that. This is the nucleus of the galaxy M87, and this is the first ever image of a black hole. Das ist das erste Bild eines schwarzen Lochs.
This is the first image of a black hole.
C'est la première image d'un trou noir. What you are seeing here is the result of many people working together. You have probably seen many images of black holes before, but they were all simulations or animations. And this is so precious to all of us because this one is finally real. What you're looking at actually looks like a ring of fire. And it's actually created by the force of gravity, by the deformation of space-time, where light actually goes around a black hole, almost in a circle. And that creates that circle that we see here. It has a diameter of, I forgot the number actually. 100 billion kilometers. Now I got it right. It has 100 billion kilometers. But actually, at the distance, at the huge distance of M87, it actually will appear as a mustard seed in Washington, D.C., as seen here from Brussels. The size of the ring is actually determined by the mass of the black hole and very independent of all the parameters of the black hole or the modeling. And so we can derive from that size directly what the mass is. And it's 6.5 billion times the mass of the sun. That is an enormous black hole that we see there. We see also more in there. We see this dark region in the middle. I've always been asked by my colleagues, or told by my colleagues, you cannot see a black hole, can you? And I think they're right. You cannot see a black hole, but you can actually see its shadow. And that's when the light actually disappears behind the event horizon, creating that dark region, that dark shadow we see there. And this is amazing if you think about it, where if you know the story behind that image, we're looking at a region that we've never looked at before, a region we cannot really imagine being there. It feels like really looking at the gates of hell, at the end of space and time. The event horizon, the point of no return. That is awe-inspiring to me at least, but it's also important for physics. I think my colleague Luciano Rezzolla will now continue and explain to us why this is so important.
Questa è la prima immagine di un buco nero. So black holes are part of our daily knowledge. In fact, even a child knows what a black hole is, and the best definition I've received actually comes from a child who simply said, well, it's just a hole you cannot fill. So they're very simple, but they're actually extremely problematic in physics, and because of the properties they have. The first property is that at their center, in a single point, we think the laws of physics break down. We call this point a singularity. Another property is that this singularity is covered by a surface, a mathematical surface, which is called the event horizon. Gravity is so strong on this surface that nothing, not even light, can leave it. And this surface separates the interior from the exterior, and nothing from the interior can leave and be transmitted to the exterior. And for a scientist, this is a drama, because scientists want to know everything about every corner of the universe. So having a region where you say you cannot experiment there, or you can experiment there, but you cannot tell the results of the experiment, is extremely frustrating and puzzling. And the same puzzling thought was shared by Einstein. So how do you get to terms? You come to terms with this idea. Well, the first thing you want to do is convince yourself that black holes exist, and in particular an event horizon exists. And the image we have produced does exactly that. So you may wonder, how do you know it is a black hole? And that is because it matches extremely well with the prediction that we can do from theory. And this is shown in this picture over here. So on the left, there is the observed image. On the right, there is a theoretical prediction. And as you can see, the analogy is remarkable. As a matter of fact, we have carried out over these last 6 months the most extensive investigation of what happens to plasma, to matter, as it falls onto a black hole. We have used supercomputers and highly advanced numerical codes to calculate what happens. And what we've learned is that as matter falls onto the black hole, it will start rotating at speeds which are close to the speed of light, and will become hot and emit light, especially in the radio frequencies, which are the ones that our telescopes can capture. But these simulations are not sufficient. If you want to know what a black hole looks like as an image, you need to take into account that light doesn't move on straight line near a black hole. Just contrary to this room, light can come from all sorts of places. And so light can be bent, can be lensed. And so the image that you obtain by looking at a black hole can be very counterintuitive. And we have carried out a very extensive investigation. We built tens of thousands of synthetic images which cover all the possibilities that we think are realistic conditions under which a black hole is formed. And this is how we have come to conclude that this is a black hole, as predicted by Einstein. Now, you may ask, what is the meaning of this discovery? For many of us, it has different meanings, but there is one meaning that we all share and is very precious to us. We have transformed a mathematical concept, that of the event horizon, something that I normally write on a blackboard when I lecture on this, into a physical object, something that we can test and we can measure and we can observe repeatedly. And you may think this is a minor thing. Actually, this is a fundamental first step in any scientific progress. It's a scientific method. Be able to make an experiment and deduce from this what are the, how does nature work? And now I'll leave the word to my colleague Eduardo Ros to explain how this beautiful experiment was first carried out.
So, astronomy is not something that you do just from your desk. In many cases, you have to embark in an expedition. And 2 years ago, a large team of astronomers embarked in expeditions to the most remote places on Earth, in places where the atmosphere is thin and dry, because we need to observe at a wavelength where the atmosphere is important. The important thing of that is, in these locations are also facilities, as you see. They're like Iran 30-meter telescope or ALMA or APEX with European technology. And in these telescopes, the team of astronomers went there, prepared with one eye into the weather forecast, checking up all the systems of the telescopes, checking that everything works, and waiting for the go command when the weather was good in all these sites around the Earth. One of the tricks you need to make such an image of a black hole is to get a telescope as big as the Earth. And to get that, the small pieces of this telescope are parabolic antennas, which you can see the locations in the picture there. These teams were observing that. We had a fantastic good luck because we get good weather all across the globe at the locations of the telescopes. These data were stored in disks because you don't have optical fibers there. You have to fill boxes of hard disks, pack them into an airplane, in some cases waiting for several months, like in the South Pole, until the winter over is gone, because it was night in April 2017. You wait them, and these data are sent to processing centers where they are played back as they were recorded and synchronized with atomic clocks. These places are like in the Haystack Observatory in Massachusetts in the US, or in Bonn, Max Planck Institute. They are the so-called correlators. Data are played back, they are evaluated, and then they are given to a further team who checks this data. Every telescope is different. You need to correct for the characteristics of each telescope, put all that together so that you get a telescope as large as the Earth. And this process needed also several months of hard work, assessment, iterations, until people were sure, okay, this is the data that now we can begin to image. We can extract the information from this precious data, which occupied 6 cubic meters of disk, as I said, to get something like the image you have just seen now. And to know how you extract this information and you get from that, my colleague Monika Mosibrocka will show us.
You may wonder how this image was made in the first place. Event Horizon Telescope data is like incomplete puzzle set. We actually only see pieces of the real true image. And then we have to fill in these gaps of these missing pieces to construct the physically possible image that is actually matching our data. This is actually a very difficult process. Therefore, the imaging process has been split into several phases. At first, at the very beginning, we were working on this imaging completely alone, each of us. This was a remarkable, almost life-changing experience to see an image of a black hole shadow popping out on the screens of our ordinary laptops. Next, we formed independent teams that work completely independent from each other to repeat the imaging process. This was very necessary, important step because we wanted to get rid of the human bias as much as possible. And in the last phase, which took the longest time, the imaging was done very, very carefully via very careful scientific analysis. So what have we learned from the images, and not just from the images, also from the data that are lying underneath this image? So first of all, we have observed this source for 4 days. Over the 4 days, the ring is there. The image looks almost exactly the same. We have also measured the size of this ring. Over 4 days, the size is always the same. It doesn't change. We have also measured the contrast between the ring itself and the central darkness. And the contrast is as large as it is expected for the black hole shadow. But there is one more very peculiar thing about this ring. It's not really a full ring. It actually is much brighter at the bottom side. Why is that? Our models told us immediately that this kind of structure can be only formed if something in the source is rotating. What is rotating? It could be the black hole, but also the matter around it, or both can be rotating. At the moment, the images are not yet sharp enough to actually estimate or calculate the exact speed of this rotation. But these images give us a sense of the direction of the rotation, which is clockwise in the sky. So to summarize, our images, our data tell us that we are looking at the shadow of the black hole, which has been predicted by all the models of the black holes that we have developed over the last few decades. And now Anton Zenzus will share some final remarks on the current state and the future of the Event Horizon Telescope. Thank you.
So my job now is to put it all together for you. The Event Horizon Telescope is a very ambitious project, but one with a very clear goal. We want to image, for the first time, the central black holes in the galaxy M87 and in the Milky Way. Today, now, 6 papers are appearing in the Astrophysical Journal Letters, a special edition, that show the image and all the discussion that is needed to convince our scientific colleagues. And in a few days, the data from our observations will be made public so that scientists anywhere in the world can verify our results. So how have we made this happen? We had to assemble a fleet, a capable fleet of the best and most sensitive millimeter wave radio telescopes in the world, combined through supercomputers to form one large radio telescope. We had to organize a team that now numbers to more than 200 scientists from many institutions around the world. This is a truly global collaboration. We cannot name all the people that are participating in this, but representative for all of them, I want to recognize Colin Lonsdale, Director of Haystack Observatory, and together with me, co-chair of the EHT Collaboration Board. He represents, together with our other friends here, the global partnership that we have, all the people that now are listening elsewhere that work together in this project. The preparation for these observations took a long time. I've spoken this morning to somebody who started 40 years ago building sub-millimeter telescopes. And so you can say several decades of preparation went into what in 2017 was for the team a very, very difficult, a complicated experiment to perform. This experiment was successful. This story is not a story of one hero. Instead, there are many heroes to this story. I'm proud to work with these people, and we salute their achievement. A number of them are here in the room today, ready to meet you later. So in Europe, how were we able to play a leading role in this endeavor? Foremost, it is through combining forces. We have brought together astronomers, observers, theoreticians, and facilities Together, we in fact were able to make a much better result than we would have been able to do individually. Of course, in Europe, we have direct access to some of the most powerful millimeter wave radio telescopes. The Institut Radioastronomie Millimétrique ERAM's 30-meter telescope was a crucial element in the north. ALMA, the Atacama Large Millimeter Array, where the European Southern Observatory is a key partner, was absolutely a game changer. It enabled us to get the sensitivity and the resolving power to make these images happen. Scientists in Europe for decades have collected the capabilities, have developed methods, have acquired the excellent skills that were needed to participate in the scientific process in this project in all places. And last, the technical development capability that we have to build instrumentation, state-of-the-art instrumentation that we need, is second to none here in Europe. Lastly, the public funds, the taxpayer money that was spent on our basic research here, both from national resources, but also from the European Union, from the European Research Council and from RadioNet, was crucial in making this excellence happen. We appreciate that very much, and we hope we can come back. So where are we going from here? M87 in the bag. We're confident that very soon we'll complete the analysis of Sagittarius A star. We will go back to observe, and so please stay tuned. We'll come back. We are already underway improving the array. Foremost, ERAM's expanded NOEMA array that they will soon finish will again be a game changer for our trade. ALMA will offer us improved capabilities. And the Greenland telescope and perhaps the African millimeter telescope project will make critical contributions to improving the quality of the EHT. With all of this, we're well placed to go into the next step of this journey. I think that we will be able to confirm a lot of the signs that we're expecting. But much more important, we will be able, with this machine, to make discoveries of the unexpected. And that's the most fascinating in science. I personally like to say that I will think of a time before and after I saw for the first time this image. You mentioned this also. Today, I believe for all of us, marks the beginning of the day after for all of us. Thank you very much for your support, and thank you for your interest in our science. Now we will be ready to take your questions. Thank you.